Okay, so we are going to look at an example problem using the idea of Bernoulli's equation in our problem. And this is it's an example out of Night, chapter 15, and it's example number 12. So we're just going to walk through that example. So, small hydroelectric plants in the mountains sometimes bring water from a reservoir down to a power plant through an enclosed tube. So, you can imagine that here we have this reservoir of water in a mountain, and there's a tube that brings that water down to a power plant. Power plant. All right. Now, let's imagine in one such plant, the 100 centimeter diameter intake tube. So this spot, I'm going to call that spot 2 for now. 2 has an intake diameter equal to 100 centimeters, or a radius, of course, equal to 50 centimeters. All right. The intake tube is 50 meters below the reservoir's surface. So there's water in this reservoir, and this distance is 50 meters. So it's 50 meters below the surface. The water drops 200 meters through the tube. So this distance is 200 meters between the reservoir tube and the bottom. Okay? And it leaves a tube to go to the power plant, the turbine, which at this location, we'll call this spot 3, and you'll see why I chose 3 in just a minute. The outflow has a diameter equal to 50 centimeters, which means, of course, the radius is 25 centimeters. All right, so that's our situation. We want to know a couple of things. First of all, how fast is the water flowing out of this tube and into the turbine? And second, what's the difference in pressure here? So, and this is where the example deviates from in your textbook. What's the difference in pressure between the intake and the outtake? So how's that pressure difference look? All right, so we're going to use this idea of Bernoulli's equation. I'm going to add one more time point or location point, as it might be more visual, and that's at the base of at the top of the reservoir. Why might I be interested in doing that? Well, Bernoulli's equation tells us that the pressure relationship, that energy relationship, is through the entire system is constant. So if I look at point 1 and point 3, that is within the parameters of that constant. It has to be constant at point 1, and it has to be the same at point 3. So let's apply Bernoulli's principle to these two locations, time points. So we have the pressure at 1 plus 1/2 the density times the speed at 1 plus the density times g times the height that 1 is at has to equal the pressure at 3 plus 1/2 the density times the speed at 3, which is what I'm interested in, remember, plus the density times gravity times 3's height. All right, if ever we're dealing with height, just like we did in conservation of energy, we have to set a reference point. So we're going to set our reference point to make sense and be helpful for us. We're going to set our y equal to 0 here at the base. What does that do for us? Well, it takes out this term because that is at my reference point 0. All right. What else can we say about this problem? Well, at the top of the reservoir, this is where the water is just starting to move. It's starting to flow down. And so the speed of the water at the very top is also 0. So that term goes away. Now, we aren't given any information about the pressure, but the pressure at 1, well, that's open to air. So it's whatever the pressure is in the air. The pressure at 3, this tube also opens up to air into the turbine, and so that is also the pressure of air. And so these two, while not 0, they are equal, and therefore in this relationship, are going to cancel each other out. And so what are we left with in terms of this relationship? We have rho times g times the initial, or the height at point 1, excuse me, plus 1/2 rho times the speed at point 3 squared. And then we can solve for it. If we solve for the speed squared, well, I bring my 2 over, my rho's go away. I end up with 2 times g times the height is going to equal to my speed. All right, so when I look at that, and I have my calculator over here, what information do we have? Well, 2 times gravity, 9.8, and what's my height? Well, I have 200 meters to the inlet and another 50 meters. And if I take the square root of that, we get our speed at the bottom of 70 meters per second. All right, so utilizing Bernoulli's equation, looking right at the top and the bottom, what's the advantage of doing that? Well, my pressures are the same there. And since I'm going to the bottom, well, that's what I'm interested in. This term goes away. And at the very top is where I'm starting just those water droplets. If you imagine a water droplet going through this process, is starting at 0. So that term goes away. It makes the problem pretty slick to solve using this Bernoulli's principal energy idea. All right. So that's part 1. Part 2 asks us what's the pressure difference in the inlet and the outlet. And so now we want to use the same relationship and look at this situation. So let me just erase the last one. If you didn't get that written down, or of course you can always rewind the videos and go through the thought process again. Okay, so for part 2, we are going to look at Bernoulli's principles examining 2 and 3 as my 2 states. So we have the pressure at 2 plus rho times 1/2, well, that's how I usually write it. Let's write it consistently. 1/2 rho times the speed at 2 squared plus rho times g times y at 2 is going to equal the pressure at 3 plus 1/2 rho v3 squared plus rho times g times y3. All right, so we're interested in the pressure difference, the difference between 3 and 2. And so we can rearrange this equation to look at that pressure difference. P3 minus P2, so if I bring P2 to this side, the difference between P3 and P2, everything here comes to this side. So I end up with 1/2 rho times the speed at point 2 plus rho g times the height at point 2. Bring this term over, minus 1/2 rho times the speed at point 3, and bring this term over, minus rho g, the height at point 3, and that's going to give me my change in pressure, which is what I was interested in. All right, so now let's look to see if any of these terms go away based on how we've set up the problem. Well, we've set our reference point 0 at the bottom, so that tells us that the height at point 3 is 0, so this term is indeed going to go away. We solved for the speed at this point in the first part of the problem. Remember, it was 70 meters per second, and I'm just going to write that down so we don't lose sight of that. That was from part 1. All right. So this term is known. The height of point 2 is 200 meters above 0, so we will know this term. I don't know the speed that the water is flowing at point 2. It's not 0, because we can imagine if we follow a single droplet of water, it comes at 0 at 1. We talked about that in part 1, and then it flows down, so it's actually flowing there. So I don't know the speed at point 2, and I need that to solve this problem. So what can I think about? Well, you can think about that continuity idea, the other principle we talk about in this introduction to fluid flow. So let's use the continuity equation to look at the speed of that particle at point 3. Now, I could look at the continuity of the bulk flow, of any of it, but we have this tube and we have this other tube. So the bulk flow, as it goes through this tube, has to stay the same, right? So we know that the speed at 2 times the area of 2 has to equal the speed at 3 times the area of 3. And so the speed at 2 is equal to the speed at 3 times the area at 3 divided by the area at 2. All right, that's our continuity equation. So we have all this information. The speed at 3 is 70. The area is pi times the radius of 3, which is 0.25 squared, divided by pi times the radius at 2, which is 0.5 squared. The pi's go away. And we have 70 times 0.25 squared divided by 0.5 squared. And we get the speed at 2 equal to 17.5 meters per second. So using the equation of continuity, remember these principles work together. It's all about fluid dynamics and fluid flow. So now we can plug our numbers in to solve for the change in pressure, or the pressure difference. So we have 1/2. This is water flowing, and so with water flowing, I can't get rid of rho. It's not in every term. It's not in that pressure term. And so we know it is 1,000 kilograms. Per meter cubed. And my units aren't working out. We don't want the unit. Anyway, I'm blanking on the unit of my density of water. Density, mass per volume, kilograms, meters cubed. All right, always go back to your fundamentals. So 1,000, I'm not going to put the units in anyway, times 17.5 squared plus 1,000 kilograms by meters cubed times g, which we know is 9.8, times the height of 200 minus 1/2 1,000 times the speed at 3, which we know is 70. So that's our change in pressure, our pressure difference. All right, so 0.5 times 1,000 times 17.5 squared gives me 153,125 plus 1,000 times 9.8 times 200. That gives me 196,000 minus 0.5 times 1,000 times 70 squared, which is 245,000, and that equals my change in pressure. And we're using standard units, so of course this change in pressure is going to be in pascals. So we have 153,125 plus 196,000 minus 245,000, and we get negative 336,875 pascals is our change in pressure. All right, so we see our pressure drop. We have a lower pressure at the bottom than we do at the top. So we see that pressure change happening. 153,125. 245,000. Yep, okay. Perfect. Just want to check my numbers. All right, so we see a pressure difference, which we expect, and we also see this relationship using continuity and our Bernoulli's equation. All right, so 2 steps to that problem. Good job.